slightly trickier, right? You should be able to do the first one. Remember, I'm only reacting one equivalent of this with one equivalent of this, right? Give you a hint. This reaction was shown on the previous page, correct? So I just rewrite in this form. So if you want to convert from this to this, you just add NaSH, correct? So now what if this N is joined to this N? You will still be joined, correct? So this is correct, but try to make it, how to say, symmetrize it, make it look nicer, right? You should have a cyclic product. Try to number the atoms if you are not confident in drawing the structure. Okay? Yeah, that's the structure, right? Just have to follow the reaction in front. So for the next two blanks, right, I've drew something here to help you. One of the blanks is this product, right? So you have to figure out what's the other blank. And one of the blank is this product, the other blank is again this product, right? So you just figure out which one, right? straightforward, right? So why does the reaction with H2S give you this product but not this product, the cyclic product? Can I explain why? Why doesn't this cyclize?
There's nothing to deprotonate this one.
Yes. Okay. H2S is acidic, correct? The reason is the same, right? Sulfur is very big. So H2S, in fact H2S is more acidic than H2O, right? For information. Due to the same reason, right? You can explain by saying that, okay, after I deprotonate it once, I'll have HS minus, this one I have HO minus, right? So this resides on a larger atom, is more stable, therefore this is more acidic than H2O, right? Anyways, if you just use H2S, you realize that there's nothing to deprotonate it because your condition is acidic. H2S is an acid, correct? So you only perform one addition, one substitution. The other one won't be substituted. And if you are wondering, right, why can't I do a SN2 reaction like that? Right, the reason is because this is not a good nucleophile when it is not deprotonated. Right, same reason as the first question. So you won't perform a SN2. And why you won't perform a SN1? Because this is a secondary, correct? So for secondary, it's actually quite risky. So you would rather not anyhow perform an SN2 or SN1, right? And then for the last blank, NaOH and H2S. So what will happen is, right, some students might be very confused when they see multiple reagents being thrown in together because they don't know which one will be added to your compound, right? But if you think about it in a logical way, right, NaOH, of course, Na doesn't do anything. So whatever is your solution is your OH minus and your H2S, correct? So imagine if I throw OH minus and H2S into my solution, what will happen first? That's always the question, correct? So we know that OH minus is a base, while just now we mentioned that H2S is an acid. So like what I always emphasize, acid base always occur first, correct? Because whatever that transfer is just a proton, which is small and there's no steric hindrance whatsoever, compared to your nucleophilic substitution whatsoever, which involves steric hindrance, correct? So therefore, acid base will always occur first. So since acid base happens first, right, and we know H2S is an acid, we know that this equilibrium will take place, whereby you will form H2O plus your HS minus. Okay? H2O plus HS minus, why do I put this sign towards this direction? Because OH minus is a strong base, H2S is an acid, correct? So equilibrium favors this side. In other words, if you add these two, actually what is present in your solution is just your H2O plus HS minus, right? So now what will happen is that your HS minus, which is a nucleophile, right, will attack one of these to become SH, right? H2O does nothing because, like what I mentioned, HS minus is a stronger nucleophile than your H2O. Because this is negative charge, your H2O is neutral. So only your HS minus will do the attack, right? So after you form this species, remember your solution, you have your OH minus and your HS minus, right? Either one can act as a base to deprotonate it. So once you deprotonate it, the second reaction, the second SN2 reaction can take place. Pretty much like your first reaction, right? So that's why for this, you will have the cyclic product. So you can see that although all these three reactions involve sulfur reagent, by slight adjustment of the reagent or the conditions, you can get different products, right? That's what I want to bring about. Then the last question, right? I remember I didn't go through this kind of question, but it's actually quite important. finish seeing the question already? Yeah, so I just go through. So you can go back and think about it again. Okay, so I'll go through first. So if you read this with your H2S, right, you see that you get the unexpected product. What you expect to get is actually this product, correct? But you obtain this product. So if you were to think about the previous question, you only have two substitution ongoing if you use NaSH, or there's something acidic that's present, something basic that's present. But how come for this case you only need H2S, right? Later we'll answer that question. So for this case, it's quite obvious that if you add this to this, right, it's a SN1 kind of reaction because it's tertiary, right? So what will happen first is this will just undergo hydrolytic fission to generate this carbocation, right? In order to get the product, the only way for you to get to a final product is by resonance, right? Whereby this goes here to form these species, right? So these two forms are actually resonance structures, and you are required, sadly for this year, to know how to draw simple resonance structures like this. Right? This is considered very simple because you only need one arrow. So what this actually means is that you have a hole here, correct? You can visualize this shifting of electrons in your mind, then you'll be good enough, right? So this is like a double bond, which is here, and this is your carbocation, which is connected only to 3 species. So there's an empty orbital above and below here. So what this empty orbital do is that you can pretend it as a hole, right? So electron density from the adjacent pi bond can actually just join to it instead, and the positive charge goes to here, right? So this shifting of the electrons, this delocalization of positive charge stabilizes your carbocation, right? Just like spreading of other charges would stabilize their species. So you have actually these two species in resonance, okay? And it's not correct to say that you will swap between these two, right? Because the real form, if you observe it, is actually a hybrid between these two, right? Just like your benzene. Sometimes it's not like sometimes you see it like that, sometimes you see it the other way, right? You always see it as this form, whereby everything is delocalized. So this is something like that, right? So next, going back to this question, in order to form the final product, what you can do is that the only thing that you can do is that you will need to take your H2S, right, acting as a nucleophile to attack this end instead of this end, since these two forms are in resonance, right? So once it attacks this end, then it's quite obvious that you will get this product. And of course, a Cl minus, right? So the next step is, of course, deprotonation to generate these species. SH. Okay, this is quite predictable. So the next question is, without the addition of base, how does it attack the other end? I won't draw the other mechanism. In other words, this one attack this one because it's the same, correct? The main question is, why don't I need a base? Right, now recall the mechanism. This is SN what? SN1, correct? Does SN1 depend how good your nucleophile is? It doesn't. Even if you add base, you get a product. You don't add base, you'll still get a product because it's an SN1 reaction. So that's why you don't need to add a base, right? So what you can do is that when you have the other carbocation, you can just attack directly. After you attack directly, right, you have these species. I won't draw the other end, right? You have these species, and remember the Cl minus they will kick out for this compound, right? You can just come in and do a deprotonation, and you'll get the final product, right? So this question is just testing you on whether you understand your SN1, SN2, as well as your resonance.
Why does it undergo the hydrolytic reaction here?
Because an SN1 reaction, correct? This is a tertiary carbocation. Some more, it can be resonance stabilized. So it favors an SN1 reaction over your SN2, because your SN2 is not supposed to occur at a tertiary center, right? And if you don't undergo SN1, you can't generate these species, because for SN2, remember, it's a direct substitution, so there's no way for you to generate a carbocation to resonate, right? So it must be SN1. Okay, enough of a revision. Let's go to today's topic. So let's try the true-false questions first, right? go back to this later, right? Let me go through first. Go through the second part, right? So just a quick, brief intro, right? You know how to classify alcohols into primary, secondary, and tertiary structures, right? And just for information, if let's say the double bond, the oxygen is directly connected to an sp2 carbon, we call it an enol, E-N-O-L, right? It's written there. The double bond with an alcohol, right? We don't classify it as primary, secondary, or tertiary, and it has other properties. It's called enol because, quite obvious, there's an in and or, right? And that's why this aromatic compound is called a phenol, right? Because it's also conjugated, correct? So both of these you'll see later that they share a few similar properties, right? Just like this compound that you mentioned the other time versus this compound, right? Why they are relatively unreactive towards nucleophilate substitution, right? Same for this. Later on we'll talk about it again. So physical properties, boiling points, they are higher because they have hydrogen bonding, while for alkane there's only van der Waals. Solubility wise, alcohols are soluble because they can form hydrogen bonds with your water. But as your hydrophobic tail grows longer, it gets less and less soluble. So therefore your ethanol is less soluble compared to your methanol, right? So now the main point for this today's lesson is about reactivity of alcohols, right? A lot of teachers don't emphasize why alcohols behave like that. Just go straight into oxidation, reaction, blah blah blah, right? So today we'll be exploring the reactivities. So if you were to look at alcohol structure, right, you have this kind of structure, and if you go ahead and fill in the lone pairs, you look like that, right? So based on this structure alone, we can predict its reactivity, right? So first, this actually resembles your water, right? So we know that water can act as an acid, it can act as a base. If water acts as an acid, what you'll get is this species, right, after deprotonation, which means for alcohol, they should also act as an acid, and they should be able to deprotonate as well, which is true, right? So their first property that we predict is their acidic property. We haven't really touched A-level stuff yet, we are just predicting based on structure similarities, right? So first is acidic property. We know that water can also act as a base because water is amphoteric. So if water acts as a base, this is what you'll get, right? So same thing, we know that alcohols, which are structural analogues of this, can also act as a base, right? So you can form these species. So in particular, what base do you call this? Lewis base, Bronsted base, or what? It's a Bronsted base. You can also call it a Lewis base, right? Because remember, your Lewis base is your widest one, your largest area, and your Bronsted base lies within it, right? So it's like a Venn diagram. So it can also act as a base, right? And we have also learned previously that water can act as a nucleophile, right? For example, in your SN1 reaction, whereby you add this to your you add it to your tertiary substrates, and then this is what you get, correct? Which means this can also act as a nucleophile. Why can it act as a nucleophile? Because there is lone pair present, right? Which allows it to act as a nucleophile. So for this, we also predict its nucleophilic properties, right? Which means it can also act as a nucleophile. Now, what else? Now, if you think about it again, right? For water, you have these species, right? This is water, right? So imagine if you introduce a base, right? Like what I mentioned just now, this can act as an acid, whereby this deprotonates it, correct? Do you realize that this resembles one reaction that you have learned? If I change this to carbon, change this to Cl, change this to OH, what reaction does it look like? Of course, plus the other things. What does it look like? It looks like a substitution reaction, correct? So we can actually classify this acid base as something like a nucleophilic substitution reaction, whereby the same arrows are involved, right? So for this case, water will be acting as the electrophile. Just like in this reaction, this species is acting as an electrophile, while this species is acting as a nucleophile. That's why it's called a nucleophilic substitution, correct? So since this species acts as an electrophile, just like this species, and we know that this species is similar to this species, we can say that this can also act as an electrophile, right, at this position. Of course, if it acts at this position, it will be an acid, right? So it can also act as an electrophile. So therefore, we can see that based on this structure alone, we can know that there are basically four roles or four identities that your alcohol can take, right? So this is pretty much summarized there, but I've only written 3 of the properties. You want to add the last one also can, right? But like what I said, a nucleophile is a Lewis base, so it's like the same thing, right? So the reactivity of alcohols have these 4 properties, and today we'll explore how these 4 properties affect the breaking of different bonds, right? Like what I wrote there, depending on what the alcohol acts as, there are 2 possible outcomes. One is that this bond breaks, one is that this bond break, right? So for example, if it acts as acid, obviously this bond break. If it acts as a base, no bond break, a new bond form. If it acts as a nucleophile, no bond break, a new bond will form. And if it acts as an electrophile, this bond will break, which is the CO bond, right? So depending on what it acts as, different bonds can break, and using this, you can predict what the product is, right? So the next few parts we'll talk about what it acts as and how it will affect which bond will break, right? So first, alcohol acting as an acid. So due to a electronegativity difference of OH bond, the OH bond is polarized just like water, so giving the hydrogen a partial positive charge. If a strong base is added, for example your NaH or your Na sodium is added, you can take away the proton, forming an alkoxide anion. And you should know that alcohols are weak acids, and thus you will need strong bases for deprotonation. And that's why you learned that your NaOH won't work, and your carbonate also won't work, because they are very, very weak acids, right? So it is obvious in the process that OH bond is being broken, right? You can represent using this mechanism. And examples of reactions that proceed in the above way are reactions of alcohol with base and metal, right? So can you try to describe the mechanism of reaction between ethanol and NaH? It's actually just copy paste the above mechanism, correct? So just for information, what do you write? Okay, you have to describe the mechanism in this way, right? So you will take the H minus to attack the H to form the alkoxide, right? So just for information, usually you learn acid-base reactions as equilibrium arrows, right? But why for this case you can write a full arrow? Remember what we say? Your NaH is actually a strong base, correct? So if it's a strong base, you don't have to draw equilibrium, because for equilibrium, it means weak acid and weak base, right? Another reason is because your H2 that is being produced is a gas, so you just escape the reaction mixture, so you won't establish your equilibrium, right? So that's why NaH is a strong base as well, because other base you just remain in the solution and equilibrate, but for this you just escape, so you push the equilibrium towards the right. So that's why it's a strong base. Right? This is related to your equilibrium. So this is quite simple, right? Next, alcohol acting as a nucleophile, or you can call it a Lewis base. It's the same idea if you didn't realize until now. Alcohols are nucleophilic because they possess lone pairs. Therefore, they can react with electrophiles. Most of the time, there is also a basic species available in the solution, which can deprotonate the charged species. So if you have an alcohol, you can react with electrophile. Afterwards, take note that you'll be charged, right? Don't anyhow remove the H without any help of any other species, right? Usually, there will be a basic species present in a solution. For example, like water. This usually occurs for aqueous solutions, or your halide, which can deprotonate the charged species. Right? So it is obvious in the process that OH bond is being broken, right? You don't break your CO bond. Examples of reactions that proceed in the above way are reactions of alcohols with your carboxylic acids and your acyl halides. And by acting as nucleophiles, alcohols can undergo nucleophilic substitution reactions, right? Usually neutral alcohols undergo SN1, deprotonated undergo SN2, because deprotonation will make your alcohol a stronger nucleophile, right? So that's why it favors SN2. And tertiary alcohols undergo SN1 while primary undergo SN2. What do I mean by this is that if let's say you have this species and you react it with this, right? You will proceed via a SN like the secondary, right? Otherwise it's quite difficult to tell, right? If I have a secondary RX and I have a tertiary alcohol, they will most probably undergo a SN1 kind of reaction. Because if this were to attack directly, it will be too sterically hindered. Right? For this case, it's my nucleophile that is being sterically hindered, not my substrate. Okay? So just take note. I'm swapping the two, right? The concept is still the same. Now if let's say I have a primary plus a secondary, then perhaps your SN2 will be favored because there's less steric hindrance. Right? So it's the same idea as your SN1, SN2. So next, describe the mechanism of the reaction between ethanol and your D species, right? If you think about it, right, it's just what I've just written, correct? Your ethanol, which is this, plus your RX. So first step is just these leaves to generate this before your ethanol comes in to do the attack, right? And you'll form these species, right? Remember the Br that you kicked out just now, right? The Br will come back in to deprotonate it and you generate the product. So it's an SN1 reaction, right? So you can see that for the second part of the reaction, right, which is this, it is just what I've just written here, right? It's the same, whereby it attacks your carboxylic ion, afterwards your Br minus or something basic comes in to deprotonate. So it's actually the same idea, right? And that's why I say don't memorize mechanism, right? Understand the mechanism and you'll see that there's not much to memorize. Everything is the same, right? Next, alcohol acting as an electrophile. So if you want to break the CO bond, it may look very tempting to just throw in a nucleophile and expect a nucleophilic substitution to occur, but like what we discussed the other time, it will work for halogenal alkanes but not for your alcohols, right? Because OH minus is very unstable. We talked about leaving group stability the other time, right? So it's a very poor leaving group and it prefers to stick to the carbon, right? Another way you can explain is by using pKb values. So if you refer to the pKb values, right, you'll realize that if let's say nucleophilic substitution were to occur for alcohol, you will generate an OH minus species. pKb is negative 1.7, while for Cl minus this pKb is 20, right? What does it tell you? Which one will be more stable? Is OH minus more stable or Cl minus more stable? Cl minus, correct? Why is Cl minus more stable? Because the lower your pKb, the more basic you are, right? The more basic you are, that means the more likely is for you to react with a proton, which means you get more reactive. Correct? Which means the reverse must be true lah. The least basic you are, the less basic you are, the more stable you are. So you can see that Cl minus is how many times more stable than OH minus based on pKb? Can you give me an estimate? So Cl minus is more stable than OH minus, correct? By how many times? This one you should know, right?
10 to the power of 21.7.
Yes, okay, 10 to the power of 21.7 times more stable than OH minus. Because each P is 10 times, because it's log scale, correct? Logarithmic scale. So that's why it's about 22 times more stable than 10 to the power of 22 times more stable than OH minus. So therefore, nucleophile substitution will only occur for the second one, but not for the first one, right? So don't ever throw in a nucleophile for the first one, right? Nothing will occur. So in order to use alcohols as electrophiles, an additional step is required to convert the OH into a good and stable leaving group before the nucleophile is added, right? Remember last time we talked about this example whereby we throw in this species, this ring, correct, with the sulfur group to convert this to this group, right, this aromatic ring, before we introduce the Cn minus, correct? That and then I ask you to compare these with this. Remember that question? Okay, this is what I mean by converting into a good leaving group, right? So therefore, in order for, if let's say you want to perform a nucleophilic substitution reaction on this, you have to convert this to something else which is more stable. You can either convert this to Cl, right, by using, for example, SOCl2, PCl5 or PCl3, or you make this into oxygen containing leaving group, right? Either ways is fine. So the main point for this is don't ever do this directly, right? So the following part is just for your information, right? Enrichment purposes. So you can either, if let's say what you want to do is you want to form this compound from your alcohol, what you want to do is you will introduce HCl, right? If it's Br, then it will be HBr and so on. So you can either introduce HX species to convert it to a RX, or for the bottom one, you can convert it to another good leaving group, right? But for now, we'll just focus on the first one, right? So for the first one, I already given you the mechanism, so you don't have to worry too much. You will take your alcohol, react with your HX. The first step will be a protonation of your alcohol to form this H2O, right? So if you want to compare OH minus versus H2O, H2O is of course a better leaving group, right? So by doing so, you allow X minus to come in to attack and to kick out H2O, because now H2O likes to leave. It's a neutral species. It's the most stable oxygen containing compound, right? So therefore it can occur now, right? So now let's look at this example, right? Alcohols mostly react with hydrogen halides in the above manner, but not with hydrogen cyanide, right? Or sulfuric acid. In other words, why we add this to HCN, right? We won't have, let's say, this one gets protonated and then Cn minus come in to attack and we get this. Why it doesn't work, right? And how come for sulfuric acid you don't get the same reaction, right? Like for example, you get O S OH, right? Why won't you have these species?
Poor leaving groups. They're all poor leaving groups.
We talk about first one first, huh? For first one, why it doesn't occur?
OH minus is a poor leaving group.
OH minus, but HCN is a somewhat acidic, correct? This is your HCN. So why can't it get protonated to form these species? Before your Cn minus come in to attack. Why can't this happen? Any ideas? Why won't X minus attack the O? Right? It's not possible for Cn minus to attack the O. Do you know why? You see, if I draw it in this way, you know that there is still a lone pair. Correct? On O. If Cn minus were to attack with this, you will generate these species. Now you already exceeded your octet configuration, so it will never attack the O, although it's positively charged. Right? They can interact by ionic interaction, but never they will form a bond. Right? So now, if we look back into the properties of alcohols, right? Now let me ask you, is water a strong acid or a weak acid? Is water a strong base or weak base? Weak base, correct? Alcohols are weak base as well, because they are structural analogues. So if this is a weak base, it makes sense to think that you need a strong acid to protonate it, correct? Now, is HCN a strong acid? No, HCN is a weak acid, correct? If you compare with all those HX species, HCl, HBr, HI, they are all very acidic, correct? So you can protonate it. But for this, you are actually using a weak acid to protonate a weak base. So this is very, very unfavorable, correct? Which means this species, although you'll be generated to very, very minute amount, or negligible in other words, right? And Cn minus, take note, Cn minus, is it a strong base or weak base? Cn minus is a strong base, correct? Because it's a weak acid. If this is a strong base, you will prefer to capture back your H versus attacking here, because it's such a strong base compared to your halide. For your halide, X minus, is it a strong base? No, because we know that HX is a strong acid, so X minus is a weak base. If it's a weak base, yes, although you can still get back, but now attacking here wins over deprotonation, right? So that's why for this it can occur, but for this it cannot occur, right? This is something related to kinetics as well. The main thing is you understand this concept and rephrase in your own words, right? So what about sulfuric acid? We know that sulfuric acid is a strong acid, but why won't it form just now the product, right? So that's my key point, right? If you add sulfuric acid, of course it will get protonated because it's a strong acid, but afterwards, remember, this is the structure of your sulfuric acid, right? H2SO4. So after it gets deprotonated, after it transfers the proton to here, this is what you'll get. Okay. So now, of course, we know that this is a weak base, right? Because it's a strong acid. So this will not attack here, right? But do you think this will attack here? If you attack here, it must act as a nucleophile, correct? Do you think this is a good nucleophile or not? The answer is no. Why isn't it a good nucleophile? Because this negative charge, okay, it can delocalize into this oxygen. It can also delocalize into this oxygen, right? This delocalization will cause your negative charge to be spread out over these three oxygens, right? That's why there's still a controversial about the actual structure of the sulfuric acid, right, after you deprotonate it. So which means you have a negative charge being spread over 3 atoms. Each atom will get about one third, right? So therefore this species is not nucleophilic at all, right? We call it a non-nucleophilic species because this negative charge is so spread out, right? So if it's not nucleophilic, there won't be a tendency for it to attack this. And another way you can think about it is that this is bulky, right? You have S connected to 1, 2, 3, 4 oxygen. S itself is really very bulky. Somehow you are surrounded by oxygen, and this negative charge is delocalized. So this makes this a non-nucleophilic species, so you won't do the attack, right? Instead, what you do is that this reaction is actually a dehydration reaction, right? If you use sulfuric acid, so you actually dehydrate the alcohol, right? Okay, so the last one for information, right? instead of using HX, you can convert it to other good living groups, right? For example, if you refer to the last point, right? Examples of reactions that proceed in the above way are reactions of alcohols with HX, SOCl2, PCl5, or PX3, right? They react in this way, whereby your CO bond is being broken. So if you were to look at the mechanism, right? The first step of the mechanism is actually the same as the reaction with HX, right? If you compare it, I'm just replacing H with an electrophile. So after the first reaction, you will generate an OE, which is a good living group. E basically, there's a variety of structures E can take, right? So I never really write what's the exact structure. So after you form the good living group, then the nucleophile can come in to attack, right? And take note, your EO minus is a stable species, right? The concept is still the same. Is the conversion of OH to a more stable living group. Okay? Let's look at the second part. Right? So lesser of those qualitative part. So electrophilic addition of steam, that's the first reaction that you have learned, right? So there are two conditions, one is laboratory, one is industrial. So for laboratory, you use corn H2SO4 before you warm it, right? To generate your alcohol, and take note that you have to consider your Markov-Cost rule, right? Whereby your hydrogen will connect to the D-substituted side and your OH will be connected to the more substituted end, right? So you have this secondary alcohol. Okay, you can either use corn H2SO4, H2O warm, or steam H3PO4 catalyst, right? So that's for addition of steam. Next one, nucleophilic substitution of your RX. You can just throw in NaOH or KOH. We have learned this reaction already, and you will generate the same alcohol, right? And most of these reactions we have learned the previous two. So the next one is the reduction of your carbonyl compounds, right? The first one is just for information, right? Because there are some people which ask me, if I reduce, you all have learned carbonyl compounds already, right? Some students ask me, if I reduce this, will I get this? Right? The answer is no. It is not so simple. If you reduce this, what you'll get is you'll get this. Right? Again, we will talk about this again when we talk about carbonyls, because you will need to analyze the mechanism before you understand why you obtain this product. Right? So now just KIV first for the first one. For the second one, it should be quite easy, right? You will generate your primary alcohol, right? So the main idea is, right, you have this compound, you just have to add, just pretend H is coming in, so you just form a bond with this, form a bond with this, so you have your primary alcohol. Same idea for the rest, right? So for your ketone, if you reduce it, you will have a secondary alcohol. And for your carboxylic acid, if you reduce it, you have a primary alcohol, right? And for your ester, if you reduce it, take note, something special about ester is that if you, let's say you have this ester, if you were to reduce it with lithium aluminum hydride, right, you obtain this product plus this product. In other words, two alcohols. So what you do is you just cut here, make this into alcohol, make this into alcohol, right? Reduction, and take note, whenever you have esters, amides, always take note, right? These R and these R, they can be connected in some way in the ring structure, so you should be able to predict what's the product as well, right? It's the same idea. Okay, so these for esters. Take note that these are all reduction reactions. Reagents, generally LiAlH4 in dry ether. H2 nickel also works, but they only work for aldehyde and ketones. And in the next chapter, we'll see what's the difference between the three reducing agents. Basically your lithium aluminum hydride, sodium borohydride, and your H2 nickel, right? What can reduce what, and how you can do selective reduction, right? Conditions reflux. Usually we'll try not to use lithium aluminum hydride because it's very reactive. It's too reactive. Sometimes it's very dangerous to handle lithium aluminum hydride because it's moisture sensitive as well, right? So the next one that I want to talk about is for information. I put it here because it's very, very common nowadays really, right? Basically you can classify it as a reaction whereby you have to learn, right? Actually there are some reactions whereby I'll classify it as not in syllabus but always tested, right? This is one of it. So for the Grignard reaction, the mechanism we'll talk more about it in carbonyl, right? Because it involves nucleophilic addition. So basically what you'll get is that, right? Right? If you add, we call these kind organometallic reagents, right? R lithium, R magnesium, right? This kind organometallic because it contains organic and metallic part. So after this, you will obtain this product basically, right? For the first one, and for the second one, you should be able to predict, right? You have this product. Right, if you use an R prime, so you see that I'm basically just adding the R prime to here and making this to OH. Right, we'll talk about this mechanism when we talk about carbonyl, right? So reagent conditions, your organometallic compound in dry ether, same thing because they're very reactive. And second step is to use dilute H2SO4, right? We'll explore this in carbonyl, so don't worry for now. So these are the reactions which involve the breaking of a CO bond, take note. So for the first one, we talked about it already in RX, right? You can use the tray combo to get what you want. Take note that for iodine, you have to use H3PO4, not H2SO4, right? We already talked about this. Because H2SO4 is a strong oxidizing agent, you oxidize I- to I2. The mechanism, I've already drawn you, and this is for your information as well, right? But you should be able to describe, you should be able to draw the mechanism given the description, like 1, what happens, 2, what happens, right? So this mechanism already drawn just now. Next, nucleophilic substitution with your SOCl2, etc. Same thing, we have talked about this the other time. And the reagents conditions are all given as well. So basically the most important thing for this is the mechanism, right? This is again for information, and it seems very complicated. Yes, it's very complicated, correct? But if you were to look at the mechanism, the first step, right, is actually your SN2 reaction, correct? Whereby it attacks the sulfur and your chlorine leaves. It's the same idea. So after you generate this positive charge species, this pyridine, right, nitrogen aromatic ring, will come in to deprotonate it, right? In fact, it just acts as a base. You can just pretend as a base, right? Followed by the third step, whereby Cl- comes in to perform another nucleophilic substitution, which is your SN2 reaction, to generate these 3 species, and finally the regeneration of your base. So the main idea for this is to convert OH- into a good living group, right? So we're actually converting it to this group, right? So it's a very good living group, right? Because, like what I mentioned just now, this Cl- can delocalize, right? So it's actually very stable. So that's the main idea, right? And in this process, you can see that CO bond is being broken at the third step, right? At the third step, your CO bond is being broken, right? While for the first one, reaction with your HX, your CO bond is being broken in the second step. So if, let's say, you understand all these mechanisms, you don't really have to memorize which one the CO bond break, which one the OH bond break, because when you draw the mechanism, you know which one break, right? So another thing for this is that white fumes generated by your SOCl2 can be used as a distinguishing test for the presence of your alcohols, but not phenols, because phenols, you'll see later on that they will not react in this way, right? So elimination. For elimination, you will use excess con H2SO4. You heat it, or you use Al2O3, which is a drying agent, right? Also under heat. So by performing elimination, you will generate your mole substituted alkene, mole substituted trans-alkene, following your Sayzev's rule, right? We also talked about this the other time. And take note of the difference in reagents and conditions between elimination for alcohol and RX, right? For Rx, can you still remember the reagents for elimination? What's the reagent?
Ethanolic.
Ethanolic, OH minus, right? And heat, right? For this case, you need H2SO4, right? Why for this you need ethanolic OH minus, this one need H2SO4 is because you have to convert this to a good living group. Cl minus itself is already a good living group, right? So therefore for this case, right, you need the acid, but for this case you need the base. That's the main difference between these two, right? And just take note, right? If let's say I have this species, let's say, and then I tell you I use excess con H2SO4 and then I heat it, what will I get? A lot of students will just say, oh, I'll get the alkene. That's all. But they forgot that there's an ester. Remember, if you heat ester in acid, in aqueous acid, right? Yeah, this is excess con. What am I talking about? Never mind. Right. Let me rephrase my question. Right. If let's say you have this species and you add NaOH, a lot of students will think aqueous, right? And you heat. A lot of students will think, oh, you perform a nucleophilic substitution and then you obtain this product. But they forgot about the ester. The ester can also react by undergoing hydrolysis. Okay? So after you hydrolyze this, you should get this carboxylate. So always look at this and think of all the possible reactions, not just the ones whereby you are familiar with, right? And this is the same thing when I ask you to propose a synthesis for a product, right? You don't just introduce reagents freely, right? You always have to consider, oh, are there any side reactions that will occur if I introduce this particular reagent? Okay? So next, reactions involving breaking of OH bond. First is your acid metal reaction, right? And you will have your metal alkoxide species, which is your ONA, right? This is quite obvious. You're using your sodium metal, so it's an acid-base reaction or acid-metal reaction. Alcohols can behave as acids by donating protons just like water, but alcohols are weaker acids than water, and this is evident from its lower rate of reaction. Or you can say that it's less vigorous, right, when it reacts with ethanol compared to water. So for acidity of alcohols, in order to compare acidity, you need to consider stability of the conjugate base. This is always your chain of thought. Always draw the conjugate base. So alcohols have alkyl groups which are electron donating. The alkyl groups will intensify the negative charge on oxygen, therefore destabilize it, right? And deprotonation is therefore unfavorable compared to water. So similarly, electron withdrawing groups withdraw electron density and stabilize the negative charge, making it more acidic. I've already given you the examples, right? Your CH3 whereby it's electron donating versus your CF3 which is electron withdrawing. And of course, both are donating and withdrawing by the inductive effect, right? Remember what you learned the other time? Inductive effect is through sigma bonds, while your resonance is through pi bonds, right? For this, there's no pi bonds, so it's quite obvious that it's by inductive effect, right? So you can use these to compare acidity of alcohols. So some things which are quite obvious, which I don't think you all have a problem, is the distance effect, right? For example, I have this. Sorry, this is a bad example. For example, this versus this, right? Which one will be more acidic? Same thing. This is closer to always deprotonate, right? This is always the case. Deprotonate and compare the stability. So this F is 1, 2, 3 bonds from this O, or this is 1, 2, 3, 4 bonds from this O, right? So this withdraws electron density stronger than this. So if this withdraws electron density stronger by the distance effect, therefore this is more stable. If this is more stable, the corresponding acid is more acidic, right? There's always the chain of thought, right? Always deprotonate it and compare stability of conjugate base, right? So for acid-base reactions, this is basically just a redox reaction. You can introduce strong bases as such. So strong bases are needed to deprotonate alcohols because, like what I said, alcohols are weak acids, correct? So if you use Na2CO3 etc., it won't give you appreciable amounts of RO minus. But take note, it is wrong to say that NaOH and Na2CO3 cannot deprotonate. They can still deprotonate, just that the amount is very little, right? Because remember, acid base is equilibrium, correct? There's nothing, when you talk about equilibrium, there's no 100% undeprotonated or 100% deprotonated, right? It's close to 100%, but it's wrong to say that it cannot deprotonate, right? So for this reaction, right, you will generate this species, right, with your Na plus. So if you react your ROH with your NaH, for example, right, you will generate this plus your H2 gas, half of it, right? Take note of the first equation as well, the first one, you will generate half a mole of H2. A lot of people write 1 mole, which is wrong, right? Where got 1 mole? There's only 1 hydrogen, right? But for the second one, depending on what you add, right, the other side product might be different. But the first one, is confirm half H2. Okay. For the next one, once again, is esterification. This reaction you already learned in secondary school, right? If you add alcohol to carboxylic acid under reflux, in con H2SO4, you generate the corresponding ester, right? So if you introduce your RCOH, you just get the corresponding ester, right? Quite simple. And it's an equilibrium reaction, take note, right? And you already, have you learned that? No, you have never learned in secondary school, right? But you have learned in A levels that by adding excess reagent, you can favor the product more. But of course, you want to add a cheaper reagent, right? So the mechanism is as follows. I don't expect you to know this mechanism, right? Because it's quite complicated. It's just put there for information, right? What I want to talk about is, in fact, example 4. But before that, let me finish the points. Con H2SO4 supplies H plus ions to catalyze the reaction as well as to remove the H2O produced, right? We always, I believe your teachers always say that, oh, con H2SO4 removes H2O, correct? But how does it actually remove H2O? They say remove, then you believe it. How does con H2SO4 remove your H2O produced? That's why I say always ask why, right? So now, there's a saying whereby it says what? Always add water to, always add acid to water, but not water to acid, correct? You have heard of this saying, right? If you are chemist, you should know this by heart already, right? Otherwise your life will be gone. Always add acid to water, but not water to acid, right? Why is this so? Now imagine I have con H2SO4 inside, correct? If I add 1 drop of water, what will happen? Or nothing will happen, or it just become diluted. You sure? Water. Remember, your H2SO4 is a strong oxidizing agent as well, right? Some more is concentrated. If you add water, what will happen? Water will be vaporized immediately, right? Now imagine you introduce a large amount of water. The reaction will be so exothermic and vigorous that basically, right, your face will be gone, right? Compared to another case, the other way around, which is you add 1 drop of acid to water, nothing much will happen, correct? Because the heat released by this is more or less cooled by water. So therefore, always add acid to water, but not the other way around. And that's why for this, your con H2SO4 can remove the acid. Your con H2SO4 can remove the water. Because as your water is produced, right, the same reaction can occur. It allows the water to be vaporized, right? And so pushing the equilibrium towards the right. And that's why we always say con H2SO4 remove water. Okay, But most of the time we try not to use con H2SO4 because it's dangerous. Instead, we'll just use excess reagents, right? So H plus catalyzes the reaction by making the carboxylic acid more electrophilic for the nucleophilic attack of the alcohol. This one we'll talk more about in carbonyl as well, right? So sometimes your silica or your zeolite is added to absorb water to drive position of equilibrium towards the right. We know silica absorbs water and silica is solid, right? So after this reaction, you can just perform a filtration to remove the silica or the zeolite, right? Zeolite is something like your carbonate. It's like it comes from a rock, right? Whereby you can also absorb water. So it functions the same way as your silica, right? Now the most important thing for this reaction is actually example 4. That's what I want to talk about, right? In other words, which bond breaks? If let's say you perform isotope labeling, you label the carboxylic acid alcohol, the oxygen with 18O, right? What will the product be? Will you get this product? In other words, right? Will you get this product? Or will you get this product? Okay, and this in fact was asked before, right? I believe your school teach the other way, right? Your school will teach this way, or draw this way, then they put a box somewhere like that, correct? But they don't teach why. These only teach you, oh, this one join to here, but they never teach you why you join to here, right? So which one you think is the product, right? Before you come to your conclusion, let's study the mechanism, not memorize. You just look at the mechanism first, right? That's the first step. First step is just the carboxylic acid being protonated by the hydrogen, correct, to form this species. And then OH minus come in to do the attack. Right, now we are at second step. The OH come in to do the attack, you form your CO bond, right? And a deprotonation step occurs for the third step. And you generate this tetrahedral intermediate. Right? Actually, there's a reason for why each of these steps occur, but I will not elaborate because that will confuse you. Right? We are just studying the mechanism. Right? So just pretend that this question is, I give you this mechanism. You never learn about the box method, and then I ask you to predict what is the product, right? So you just have to study a mechanism and see at which point in time this CO bond break or this CO bond break, right? So now if you look at the fourth step, the OH gets protonated, and what happens is somehow a spontaneous kicking out of the H2O in the fifth step, right? Correct? And you see that in the last step, your intermediate gets deprotonated, right? Now what's important is the second step, right? You see that for second step, the O comes in to do the attack and you form a new CO bond, right? So if you form a new CO bond, that means which bond must break?
The double bond.
Which is this double bond, right? And another way you can think about it is the third step, the fourth step, right? For the fourth step, because for now you never label anything, right? But if you were to label it, right, for the fourth step, you look something like that. Now I'm replacing the fourth step with this, right? It's actually the same, just that I'm changing this to 16, which is what my question is telling me, and changing this to 18, which is what the question is telling me. Right, and based on this step, I know that, right, this gets protonated. This is not a new mechanism. I'm just basically copy pasting what was given. 16, 18, H2 plus, right? Followed by the fifth step, which is the kicking out of this oxygen containing 18, right, to generate eventually this species. And it was 16O. And finally, the last step. Right, so based on this mechanism, I know that it will be retained here, and what is actually breaking is actually this bond, right? If you don't understand this mechanism, don't worry, you can fall back to the square method, right, whereby your teachers teach you. Just that this one explains why is that bond that's breaking, right? I prefer to understand the concept rather than use some analogy to memorize, right? So this is just for your curiosity's sake, if you are curious, right? 15, so it's actually like that, right? This that has been kicked out, if you wish. That's for esterification. And now esterification, condensation, you can use your RCOCl as well to perform your esterification, right? Take note that this reaction is not reversible, right? Irreversible. Huh? So you obtain the same product, but it's an irreversible reaction, right? And you can perform it at room temperature without any catalyst, right? So now the question, and this is the mechanism, this is for information once again, right? You perform a nucleophilic attack. You realize that this is something related to your nucleophilic addition, right? The first step. So the first step is in fact a nucleophilic addition, but for a second step, for a nucleophilic addition, for a second step is a protonation reaction, but for this is a kicking out of your Cl minus, right? That's the main difference. Again, this is just for information, right? If there's a need, then we'll talk about it next time, right? So example 5, which esterification method above is more preferred? Right? Is it reaction with your carboxylic acid or your RCOCl?
It's all correct.
Okay, why?
There's a higher U.
Yes, because it's irreversible, right? But does that mean I can always use RCOCl? Why? Because higher U means that your RCOCl is more reactive, right? Sometimes you don't want to introduce such a reactive reagent because it might react with some other groups, right? In fact, if you were to look at your drugs, you seldom see acyl chlorides, right? Because by the time you put in your mouth, it's gone already because it's so reactive. It can just be hydrolyzed by water, okay? But for esters, no, right? It's more stable, right? Next, oxidation. Just now we talked about reduction, right? Now, oxidation, same thing, right? Remember for just now we talked about this, right? Holding hands, this H, originally holding hands with each other and then hold hand with like that. Now they just break, right? Holding hands and they hold with each other instead. It's just a reverse. So for the first one, for the primary alcohol, if you oxidize it, you will have your aldehyde first. And take note, this oxidation is strong, and you will immediately be oxidized to your carboxylic acid, right? And for the secondary alcohol, you will be oxidized to your ketone, and for your tertiary alcohol, you won't be oxidized, right? So you can use this to differentiate between primary, secondary, and tertiary, right? But you cannot differentiate between primary and secondary, right? And for this, you can either use K2Cr2O7 or KMnO4. You will see different color change for each. One is orange to green, the other one is purple to colorless. Unless you use it under alkaline conditions, whereby you will get the brown MnO2 precipitate. And that's for a second reaction, which is your mild oxidation. So for mild oxidation, one thing to take note is that in order to get the aldehyde, you have to distill it halfway, right? So you have to use K2Cr2O7, dichromate, dilute H2SO4, heat and distill, right? Or you can use MnO2, dilute H2SO4, but this one is just for information, right? So please just use the first one. So the second one is in case they give you this reagent, right? So it won't be stunned. So you'll see some observations that you'll see orange solution turning green. The second one is brown precipitate turning colorless, right? You are doing this reaction because MnO2, after you oxidize it and in the presence of acid, you'll become you become, let me see, Mn2+, right? Just like your KMnO4. After you oxidize your alcohol using KMnO4, you get Mn2+, correct? So for this same thing, you'll get Mn2+, which is colorless, right? So that's why it's brown to colorless. Colorless is because of your Mn2+. So oxidation involves the loss of one or more hydrogens from the carbon-bearing OH group. KMnO4 can be used in basic conditions, while K2Cr2O7 works only under acidic conditions. So you can actually use oxidation to differentiate your alcohols since they give you different observations. right? And this is just a summary of what you will get if you oxidize different alcohols, right? So next, iodoform reaction. You will learn even more about iodoform reactions for your carbonyl compounds, right? For this, we are only focusing on alcohols, right? So for the iodoform reaction, right, remember what your teachers always tell you, you need to have those special kind of structures, correct? So the first special kind of structure is this kind, right? Right, which means that if this is a hydrogen, it will be ethanol lah, basically. This is ethanol, correct? If this is hydrogen, so this will give you a positive test. And if this is other groups, it's just a secondary alcohol. Or you can call it a terminal secondary alcohol, right? It can also give you a positive test. Basically, this is what the first one and the second one is trying to say, the first two. And you can have your carbonyl compounds. If you have learned carbonyl chemistry, you know that carbonyl compounds also give you positive tests, right? So, in fact, for the last three, I don't think you have seen them before, correct? Last three examples, but they were asked. That's the setting, right? You can refer to prelim questions. They expect you to know the mechanism, in other words, right? Because the last three was tested, right? You will see these kind of questions when we do carbonyl. So before we talk about the product, right, same thing, I prefer to go into mechanism, because once you understand mechanism, you will know why the bottom three are accepted as well. And this is why students who understand the mechanism can do this kind of question, because they know why the last three can, right? So now, how this reaction proceed, right? Just give you a quick, brief intro, right? If let's say you have this carbonyl compound, right, and you introduce NaOH, something can occur, right? Now imagine if let's say I have a carboxylic acid and I throw in NaOH, what can occur? We talk about this first, right? What do you think can happen if I add this to carboxylic acid? This is a base, correct? This is acid, so acid base, correct? So this acts a base, this acts as acid, and I will generate this species. Correct. Now, why are carboxylic acids acidic? You have learned this? Have you learned carboxylic acids? You have learned carboxylic acids now? Is it? Learning now, right? You should know that because this is delocalized, correct? So that's why it is stable, because you can draw these kind of resonance structures, right? So now this structure is actually very similar to this structure, just that I'm replacing O with a carbon. So the same thing can actually occur, right? Whereby this OH minus comes in to deprotonate it by the same mechanism, and have here CH2 and a minus charge. Originally I have 2H, so that's why I say H2 minus. Same thing, these can resonate and become stabilized. Right? So same idea, right? So now the main point is not about this, the comparison between this. It's about what actually happens, right? But I need to make it easier for you, so that's why I relate it to carboxylic acids, right? So once you understand this good enough, we can proceed on to the next stage, right? We know why this is acidic. This is also known as the alpha hydrogen, because this is the alpha position, right? Alpha. So the next carbon, if there is any, will be called beta, gamma, and so on, right? And just for info, recently there's also a lot of questions related to alpha carbon chemistry, right? Including this. So anyways, after you generate this species, right? Remember, you have I2 in your solution, right? We have learned in alkenes chemistry that if you add this to this, what happens is that this can act as a nucleophile to attack this to form a carboxyl ion, correct? Because this is an electrophile. So now same thing can occur whereby this acts as a nucleophile and this acts as an electrophile. So after this reaction, you obtain this product with an I. Okay? So far so good, right? So now, because your NaOH is still present in your solution, right, and you still have an alpha hydrogen here, this process can repeat. So eventually, right, I won't draw the mechanism because it's just a repeat, right? Eventually, you have all the hydrogens here being substituted for iodine. So you have 3 iodine here, eventually, right? So now you might wonder, how is CHI3 generated? So for now, we know that there are no more alpha hydrogens and we cannot perform the reaction already, right? So what will happen now is OH minus, right, which now acts as a nucleophile because there are no acids present here. You attack here pretty much in the same way as nucleophilic addition, right, to form this species. This is just a nucleophilic addition, by the way, right? CI3, right? So now we see that we are turning from a sp2 center to a sp3 center. On top of that, iodines are very, very large. They are very, very bulky. So there's an increase in steric hindrance here. Increase in steric hindrance, and you will be unstable. So it can stabilize by forming back an sp2. If you form back an sp2, it must kick out CI3, which is the bulky group, right? So what you do is that this will come back down to kick out this CI3. Again, this mechanism is just for information, right? So once you kick out this CI3, you will form back this CO double bond plus the OH, and of course the CI3 minus, which you kicked out just now, right? So now CI3 minus can now act as a base, right, to deprotonate this hydrogen. So once this deprotonation is done, is complete, what you'll get is this carboxylate plus your CHI3. And that's how your CHI3 is obtained, and that's how your carboxylate product is obtained. Right? Now the main point for this is, why do the bottom 3 react in the same way? Because this is all your intermediate. If they are formed and they react, there's no reason why the bottom 3 cannot react, right? So that's why the bottom 3 also react, and all of this reacts to give you your carboxylate, right? So that is the main idea. And now the question is, why alcohols can react in the same way? Can react in the same way, right? So for alcohols such as this, the first step that actually happens is actually an oxidation step. Remember, your iodoform reaction is an oxidation reaction, right? So this actually gets oxidized to this first, and this is similar to the third one. Same thing for the first one. For the first one, right, this undergoes an oxidation to form this first, and this also contains that special structure which allows you to undergo your iodoform reaction, because there is an alpha hydrogen, right? So this is what the iodoform reaction is talking about, right? Interesting, right? Actually, for all of these mechanisms, you can just Google it online, right? And it's not required, just that you have to understand why the bottom 3 will react in the same way, right? So let me go through the next page. So reactivity of phenol or enol and oxygen. Phenols and enols have a range of reactivities, and they can behave as an acid or a weak nucleophile or a Bronsted base, right? You can analyze it using the same way as what I did, but you realize that one of it is gone, correct? Later on we'll see which one. So generally there are 2 possible outcomes. One is that the OH bond breaks, another one is that the unsaturated ring undergoes a reaction, and then you realize, hey, there's actually another reactivity that is gone, right? And remember just now we talked about its outcome depends on its reactivity, right? So you should know how to relate these two already. So now if you compare the reactivity of alcohols versus phenols and enols, you will realize that the CO bond in phenol and enol does not tend to break. And phenol and enol are not electrophilic. Basically, these are the two, right? They are gone. The above observations is due to two factors similar to those discussed in hydrogen derivatives. First is your electronic effect, which is your delocalization. You can see that from the diagram below that, right, the p orbital is parallel to the ring of p unhybridized p, a ring of p unhybridized p orbitals, so they can overlap sideways, and this results in delocalization of the lone pair. And the CO bond will have double bond character, right? So when you have got a double bond character, it will not break easily. Another thing is your steric effect, right? Due to electron-rich ring, it hinders the backside approach of the nucleophile by electronic repulsion. So that's why they are not electrophilic, and your CO bond doesn't tend to break. Okay? So due to the stronger CO bond, phenols are not involved in reactions involving CO bonds. Therefore, it does not react with your PCl5, SOCl2, HCl, HBr, blah blah blah, right? Because CO bond is strong, therefore all those reactions which involve breaking of a CO bond in alcohol doesn't apply here, right? Which means all your other reactions should still work for phenol, right? So you don't really have to memorize what reactions work, what reactions don't work. You just have to understand the mechanism and understand which one involves breaking of CO, which one doesn't, right? So some reactions that they will undergo, first is acid metal or acid base. You can either use sodium or your NaOH, right? Take note that for this case you can use NaOH because phenols are more acidic, right? So you can go ahead and draw the product, which is just your ONA. And a lot of times scientists try to save time, they just write it as like that, pH, right? They just abbreviate this with a pH. Stands for phenol, right? So for example, phenol, they will write PHOH, save time, right? But anyways, phenols are acidic, right? So again, to compare acidity, we need to consider the stability of the conjugate base, which is the anion. So what you do first is, of course, deprotonate it. Phenols have a benzene ring connected to oxygen, p orbitals overlap, and this allows delocalization of the negative charge. So stabilization occurs, and this favors your deprotonation, right? If electron withdrawing groups are attached, withdraws the electron density and stabilize the negative charge more. And if electron donating groups are present, you will destabilize it, right? I've already given you that two examples as well. Next, esterification, same thing as alcohols, right? But for this case, take note that you have to deprotonate it first, right? By using either sodium or your NaOH, right? Before you add your RCOCl. So phenol is a weaker nucleophile than alcohol due to the delocalization of the lone pair into the benzene ring. For your alcohol, there are electron donating groups, but for your phenol, it is delocalized. So since it's less available, it's natural to think that I must make it a better nucleophile in order for it to attack, right? Just like what we did the other time, whereby we have nitrogen nucleophile and oxygen nucleophile on the same ring, correct? And then I ask you which one will react first. The answer is this, because it's more nucleophilic. In order for this to react, you have to deprotonate it to make it more nucleophilic. So this is the same idea, right? And next part. Since esterification involves nucleophilic attack of the alcohol by forming the phenolside anion first using a sugar base, its nucleophilicity is increased and is more likely to react, right? This was once asked before in A levels to explain why you add Na or your NaOH, right? This is the reason why, to make it more nucleophilic, right? So carboxylic acids, on the other hand, are much less electrophilic than acid chlorides, hence they won't react with your phenol, right? They know that this is more reactive than this, right? So since your phenol, which is already low in nucleophilicity, right, you only react with this, and of course you won't react with this. For your alcohol wise, right, normal alcohol, this is very reactive, so of course you can react with both of these, right? It also makes sense to think that if alcohol reacts with this, it must react with this, because this is even more reactive than it, correct? It's quite logical, correct? So example 6, right? It was stated that due to the weak nucleophilicity of phenol, phenols do not react with carboxylic acids, but a student claimed that he could convert it to a phenoxide anion first, making it more nucleophilic before reacting with a carboxylic acid, right? So will this method work? In other words, he's trying to propose this, right? Since phenol itself doesn't react with it, correct? Why not I deprotonate it, make it more nucleophilic to attack it by using the same idea as just now? Can it work? What do you think? Again, take note, phenols are weak acids, correct? So if it's a weak acid, the base will be a strong base, right? Like what I said, acid base always occur first. If you add a strong base to carboxylic acid, what will happen? Deprotonation will occur, and you obtain this product instead, plus a phenol. So this reaction will not work, right? Take note that this concept only applies to your RCOCl, which is your acyl chloride. Okay, so that's why it won't work. Next, reactivity of phenol at the benzene ring. Since the lone pair on oxygen is delocalized into a ring, OH is acting as electron donating group, right? By the resonance effect, take note, right, which activates the benzene ring, making it more nucleophilic. Therefore, any electrophilic substitution reactions will be more likely to occur since the ring is more rich, require milder conditions, and you require weaker or no catalyst since it's activated, right? So some reactions. First reaction is your bromination, right? You can perform bromination. You have learned this already, right? If you perform bromination with your aqueous bromine, you get the tri-substituted product. Okay, 2,4,6 tri-substituted product, and if you use Br2 in CCl4, you get the mono-substituted product, either the 2 or the 4, but you'll be more favorable at the 4 due to less sterics, right? So now a lot of schools, once again, they teach one in aqueous, one in CCl4, but they never teach why one gives tri-substituted product, one mono-substituted product, correct? Have you wondered why? Or just memorize only? Just memorize. That's not the way, man. So let's look at example 7 before we talk about the solvent effect, right? So compare the bromination of methyl benzene and phenol. What are their differences, right? If you can recall, for phenol, for methyl benzene, if you were to perform chlorination, you will use FeBr2 and your Br2, right? But for your phenol, you don't need this catalyst. That's the difference. And for this, you need to heat, right? For this, you don't need a catalyst, precisely because the ring is more activated than your methyl group, because your OH is a stronger electron donating group than your methyl, right? So that's why that's the main difference, right? Sorry, not Br2, Br3. So that's why it's like that, right? So now we are curious more about the we're more curious about the solvent effect, right? Why different solvents favor different products, right? I bet not a few teachers know the explanation behind this, right? So now I'm not joking, right? They just memorize also. So let's say I have this. Same thing, we need to analyze the mechanism, right? So I believe you all know this electrophilic addition mechanism, electrophilic substitution mechanism, right? So I will not elaborate. Take note, this is for phenol. For phenol, you don't need to use the catalyst. So the mechanism is slightly different from that of your benzene and your methyl benzene, right? This is slow. Next step, ER minus comes in. This is fast. Okay. You can show off to your teacher once you learn it, right? And your teacher will be like, wow, I didn't know that. I've learned chemistry for the past, 30 years, but I never learned this, right? So this mechanism pretty much you have learned before, right? But the most important thing is not about this, it's about the energy profile diagram, right? For this, we know that I have a starting material, right? The first step is a slow step, which means that mountain is very high, followed by this intermediate, followed by a lower mountain, followed by a product, right? So now this is your intermediate, right? For intermediate, is it charged? Is it charged? Correct? It's positively charged. So I just put a positive here. For this is neutral. What about your transition state? If your intermediate is charged, your transition state, which transits from here to here, will also be charged, because the positive charge is growing. For here, the positive charge is disappearing, but your positive charge still exists, right? So for these, I'll write a positive plus here, positive plus here. These are transition states, right? So now, recall what we learned in SN1, right? Why SN1 reactions are favored by protic solvents, right? What are protic solvents? Protic solvents are those with lone pair, correct? On your oxygen or your electronegative element with a hydrogen connected to it, correct? If you have such species present, it can actually stabilize this by, remember what we talked about? What interaction is this? This is your lone pair and charge interaction, right? And this stabilization will lower the energy levels of this, right? So these energy levels are actually lowered. And it doesn't lower the starting material or product because they are neutral. You only lower this part, right? So after the first addition, right? After the first addition, remember OH is electron donating, but Br is electron withdrawing. So your this ring is actually deactivated, right? So if let's say the mountain gets too high, your second addition won't occur of your Br, right? Yes, not addition. Second substitution of Br won't occur. But now if you use this solvent, it actually helps to stabilize this positive charge, right? Which means it actually lowers your mountain, right? If it lowers your mountain, there's less energy to overcome, therefore your second reaction can occur, right? Because this helps to stabilize it. But once you change it to CCl4, right? Does CCl4 has lone pair? No. CCl4 is a non-polar solvent, correct? If you change it to a non-polar solvent, what you will do is that there's no longer this stabilization, right? A non-polar solvent will actually, remember what you have learned before, light dissolves light, correct? So a light species will most likely stabilize a light species. So for this case, we know that CCl4, which is non-polar, less polar, will more or less stable the less charged species, which means it's your starting material and your product. Which means instead of stabilizing the transition state and the intermediate, they're actually stabilizing your starting material and your product. So you realize that now the mountain is even harder to climb, which means after the first addition, the second substitution won't occur, because now you have to overcome an even higher mountain without any stabilization of anything. So therefore, the two solvents will give two different kind of substituent products, and that's the reason for the solvent effect, right? So if you are confused, you can always think about this energy level diagram that I told you, right? In fact, there's nothing much to memorize. If you understand the concept, right, you can do example A. If I change it to CS2 solvent, what do you think it will become? Will you get the monosubstituted or the trisubstituted? So we know that in polar solvent, it will give you the trisubstituted, correct? In non-polar solvent, it will give you the monosubstituted. But for CS2, is it a polar or non-polar? CS2 is non-polar, correct? This is the structure of CS2, just like CO2. Correct? So CS2 is non-polar. You have learned this in chem bonding, right? So it will give you your monosubstituted product. Same reason. Right? And of course, other factors also is going to affect, like temperature. If you use higher temperature, it will give you the trisubstituted product for the same reason. Right? Because more of them have energy to overcome the mountain. Right? So you can see that organic chem is also related to your chem energetics and your kinetics. Right? So let me just finish the other parts. Electrophilic substitution, nitration, right? You can perform it with con HNO3 or dilute HNO3. It's pretty obvious which one will give you the trisubstitute product, correct? It will be the con one. Or for this one, you're using concentration effect to push the reaction, right? Because you know that NO2 is electron withdrawing, right? So you're actually using con HNO3 to push the reaction. And unlike in electrophilic substitution of benzene and alkyl benzene, your H2SO4 catalyst and high temperature is not required because your ring is activated by your oxygen, right? So if you compare the nitration of methyl benzene and phenol, I already said, right? You don't need H2SO4 and you don't need heat because phenol, right, is more electron rich than your methyl benzene, right? And lastly is your chelation reaction, right? You will learn more about chelation in the last chapter of transition elements, right? So for chelation, you are using neutral FeCl3 aqueous, right? And what you obtain is this product, right? You know lah. 6Fe3 minus, right? If you want to draw this out, is Fe connected to OPH, 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 PHO. pH is a phenol, which is this group, right? Overall 3 minus, right? When you learn transition elements, you'll know why this will give you a violet color, right? Why are transition elements mostly colored, right? And you'll learn how to draw structures like this, which is probably, you're gonna probably learn it like, I think, May or July, right? So now the question is, why must FeCl3 be neutral? What will happen if FeCl3 is used directly or if the condition is too basic? Okay, you have learned that FeCl3 is acidic, correct? So in solution, FeCl3 is gonna dissociate to form Fe3 plus and Cl minus. So Fe3 plus, like what we learned in ionic equilibrium, under salt hydrolysis, we have learned that small and highly charged species will hydrolyze water, correct? Whereby this, right, in water you form this species, by the way, H2O6. 6 of the water will surround it, right? So what will happen is, you can lose a H plus to form Fe H2O5OH 2 plus, right? And so on until it becomes neutral. So a solution of FeCl3 is actually acidic, right? But why we can't just use FeCl3 directly? Why must we add a little bit of base to make it neutral? Right? Remember this equilibrium? phenol is a weak acid, correct? So the equilibrium is like that. If we just use FeCl3, it gets too acidic. Equilibrium will shift here. None of this, not saying none, very little amounts of this will form. If very little amounts of this will form, how can you form this complex? Whereby you require your OPH, which is this species, correct? So that's why you will need your this thing to be neutral, so that you can form this, right? And next, if so, then why can't you make it basic? If you make it basic, then you will have more of this, isn't it? But the thing is, remember for your QA, qualitative analysis, if you add base to Fe3+, what will happen? You have your precipitate, correct? What color is the precipitate? Can you still remember? FeOH3.
Dirty green.
Is it dirty green or reddish brown?
Reddish brown.
Right. So you won't have this thing, right? So that's why you have to use neutral FeCl3, but it can't be too basic, right? So that's all the whys for this reaction. Okay, you can